Alright, so hopefully this particular video will be basically almost entirely review with a little bit of preview in terms of sort of what's coming up. So let's start again by thinking about forces. We said forces is something we dealt with in 221. It's something we know we're going to deal with in 222. We know we're going to need to draw free body diagrams when we're dealing with forces, so let's just sort of remind ourselves of what all this is. So what is a force? Well, a force is an interaction between two objects, right? So I need two things pushing or pulling on each other. So how one object pushes or pulls on another tells me that there's a force involved. Again, force is a vector, so the magnitude matters and the direction. And so there's sort of we can talk about the types of forces that we're going to deal with in terms of thinking about two categories. So we can talk about contact forces, and we can come back and talk about non-contact forces. So let's think in terms of just sort of the simplest situation where I've got just a box sitting on some horizontal surface. And so because my object, right, I'm interested in drawing the free body diagram of the box. That's going to tell me, that's going to be a vector diagram showing me all the forces that act on the box. And so since the box is in contact with this horizontal surface, then I know that there's going to be a normal force. That normal force is going to be perpendicular to the surface. So since the surface is horizontal, the normal force is going to be vertical. And in this case, since the box sits on top of the surface is helping hold the box up. So the normal force points up. Now, this is really just one component of the contact force between two surfaces. I might also have friction. So in this case, if I want to think about friction, well, let's say I start pushing the box to the right. Then I'm going to need friction to oppose how I'm trying to push the box. Now there are two types of friction. There's static friction and kinetic friction. Static friction I'll get if I push the box but don't push it hard enough for the box to move. So static friction occurs when there's no motion of the object relative to the surface it's in contact with. So I can push a little bit, but the box still doesn't move because it's being held in place by static friction. Or if I push harder, then the box does start to move, and now I need kinetic friction. So if I push hard enough so that the box moves off to the right, then kinetic friction will point back to the left. So all this, the normal and the friction force, are really just what's going on when I have contact between surfaces. Next, well, what I can do is I can deal with a tension force, right? So the tension force, the easiest way to think about a tension force is tension forces happen when things pull. So why don't I tie some string off to the front of this box and pull off at some angle? And so if I do that, then I'll have a tension force. And again, notice that the tension force lies along the angle, the string that I'm pulling with in the direction that I'm pulling. So our contact forces between surfaces, usually those are telling us about pushes. Tension force usually is telling us about pulls. If I were to take my box and hook it up to a spring, then I would also have an elastic force that acts on the box once I push the box so that the spring is no longer at equilibrium. Since there's no spring here, I don't have to worry about an elastic force. I can also talk about applied forces, and applied forces are really just our way of saying, does anything else push on the box? And sure enough, in this case, I am. So this force we would probably label as an applied force, or at least that's one way to deal with it. So all these are sort of contact forces. There's another set of forces known as non-contact forces, and again, what we'll see is these non-contact forces really come from fields. We hinted at that last semester in 221. Now we're going to be explicit about it dealing with stuff in 222. So the first one we can deal with is the weight of the box. Again, weight is a force. It's another way of saying the gravitational force. In this case, since we're talking about the gravitational force due to the Earth pulling the box down, I'm going to have a weight force that pulls down. The other two non-contact forces we didn't deal with in 221. These are what we're going to deal with in 222. So I can have an electric force if I have an object in the presence of an electric field, and I can have a magnetic force if I have an object in the presence of a magnetic field. So our non-contact forces, right, gravitational field, electric field, magnetic field, these are all related to what goes on with fields, and we'll talk about this much more as we go through the semester. So if I'm setting up the free body diagram, again, well, that's basically what we did on the last slide, but there's a series of questions that, as a general rule, we can ask to help ourselves set up that free body diagram. So the first question is, does the object have mass? If the answer is yes, then we probably need to put in a gravitational force. If that gravitational force is due to the Earth because we're sitting on or near its surface, then the magnitude of that force is going to be equal to mass times 9.8 meters per second squared, and it's always going to be directed down. Is the object in contact with the surface? Well, here again, if the answer is yes, then I know that I'm going to have a normal. The normal force is going to be perpendicular to the surface. Then I have to ask a follow-up question that says, is there friction between the surface and the object? So if they're in contact, I know I have a normal, right? So if the object is in contact with the surface, I know I have a normal. And if my object, or if my surface isn't frictionless, then I will also have friction. So if I have friction, then the next question I need to ask is the object moving relative to the surface? This is going to tell me what type of friction force I have. So if the object is moving relative to the surface, then I'm going to have kinetic friction. If it's not moving relative to the surface, so it's stationary, I have static friction. If I have kinetic friction, I know how to calculate its magnitude. So this is kinetic magnitude of the force of kinetic friction is equal to mu sub k, the coefficient of kinetic friction, times the normal. Magnitude of static friction, again, this is a variable force. It can be as small as 0. It can increase up to some maximum value. So the maximum static friction can ever be is going to be given by the coefficient of static friction times the magnitude of the normal. So this big N here is just a way of saying the magnitude of this normal force. In which way does the object move or want to move? So this is telling me which type of friction force I have and what I need to do about the magnitude. The second question here is telling me about direction. So I know that friction is always going to be parallel to the surface. It's always going to be along the surface. If I have kinetic friction, it always opposes motion. Static friction opposes the motion that would occur if the surface was frictionless. So in the example we were looking at before, where I was trying to push the box to the right, well, if the surface was frictionless, the box would go to the right. So that means I need static friction to oppose that motion that would occur if the surface was frictionless. So one thing to emphasize here, notice that some forces we have a way to calculate its magnitude. So we can calculate the magnitude of the gravitational force on or near the surface of the Earth. We can calculate the magnitude of the force of kinetic friction. We can calculate the maximum allowable value for the magnitude of the force of static friction. Okay? But there is no simple expression for calculating the normal force. If my static friction isn't at its maximum value, I don't have an equation to calculate it. So sometimes we have a magnitude equation, sometimes we don't. And we just need to keep that in mind, that we don't have a magnitude equation for all forces. So the next question I can ask is there a string, a rope, a chain, a cable, etc. pulling on the object? And if there is, then I'll need a tension. That tension is going to be directed along the rope, and again, notice the tension, there is no magnitude equation. Right? Next question, is there a spring connected to the object? Again, if there is, then I have a spring force. its direction will always point back towards equilibrium, right? The idea of a spring is trying to get you back. The spring always wants to get back to its equilibrium point. So the spring force it generates will always point back towards equilibrium. The magnitude of that force will be equal to the spring constant times some length that you've either stretched or compressed the spring. So this gives us the magnitude, this gives us the direction. And then the last question that we asked in 221 was, is there anything else exerting a force on the object? And if there was, then basically we would have some applied force that we would then draw into the free body diagram. So again, with this set of forces, notice there is no magnitude equation for the tension, there is no magnitude equation for the applied force. Either you got to be told what those are, or you need to use Newton's second law to solve for what they are. Alright, so in terms of a couple just very simple examples. So here I've got a box of mass m that slides to the right across a rough horizontal table as it's pushed by a force that angles 30 degrees below the horizontal. So here's my applied force already drawn into my picture. And so as with all good vector problems, we're going to start by making the picture. And then we're going to go ahead and make the free body diagram. So make our vector diagram here. So I'm going to walk myself through that series of questions. So does the box have mass? Sure enough, box of mass m. That means I need a gravitational force. That gravitational force is going to point down. Is my box in contact with a surface? Yes, it's in contact with a rough, so I will need friction, horizontal surface. So the horizontal surface means that I need a normal. That normal will point vertically because it's got to be perpendicular to the surface. And since the box sits above the surface, that normal is going to point up. For friction, so I know I need friction because I have a rough surface. And so the next question becomes, what type of surface do I need? And I'm told that the box slides to the right. So there is a velocity. It's moving, which means I need kinetic friction. Kinetic friction is going to oppose the motion. So kinetic friction is going to point in the opposite direction of that velocity vector, which means the kinetic friction will point back to the left. So do I have a string or cable or chain connected to the box? The answer is no, so I don't need to worry about a tension. Do I have a spring connected to the box? The answer is no, so I don't have a spring force. Is there anything else pushing on the box? Yes, there's this applied force. And again, I'm told that that applied force has a direction 30 degrees below the horizontal, so that's the way I need to put it into my free body diagram. And then whatever its magnitude is will be what that magnitude is right there. So here's the free body diagram for this box in this situation. One more simple example. So now I'm told I got a box of mass m that rests on a frictionless plane inclined at a 30-degree angle above the horizontal. So again, here's my plane inclined at an angle. A rope that runs horizontal to the plane, so here's my rope, is connected to the box and tied off to a wall. So the box is just sitting there, it's not moving. I've got a frictionless plane, I've got a rope. So here's my picture. Again, let's go through our questions to draw our free body diagram. So does the box have mass? Yes, it does. So there's going to be a gravitational force that points down. Second question, is my box in contact with the surface? Yes, it sits on an inclined plane. And now because my plane is inclined at an angle, that means the normal also has to be inclined at an angle. So the normal actually points off at a 30-degree angle. Do I need friction here? No, I'm told I have a frictionless surface, so I don't need to worry about friction in either of its forms. Is my box connected to a rope or string or cable or chain? Yes, it is. So it's tied off by this rope. The rope points back up the incline. That incline's at a 30-degree angle, which means the tension force has to be at a 30-degree angle. Is my box connected to a spring? No, it's not. No spring force. Is there anything else pushing on the box? Again, in this case, there's not. It sits there basically because it's tied off by the rope. So there's not another applied force to draw in. So in this case, here's my free body diagram. I just have these three forces. So what we're going to add, again, just sort of previewing here, what we're going to add in terms of drawing the free body diagram is basically, we can go through the set of questions we had, And then we're going to sort of, before we ask about are there any other forces acting to deal with applied forces, we're going to come back and have a couple additional questions that we might need to think about to make sure we've got the right free body diagram. One of those is the object charged and in an electric field? So we'll see that if that's the case, then what I'm going to have is I'm going to have an electric force, and the direction of the electric force will be related to the direction of the electric field. And we'll talk about how this equation tells us specifically whether that force points in the same direction or the opposite direction as the electric field. I might, if the electric field is due to a point charge, then I have a particular way that I'm going to be able to calculate the magnitude of that point charge. And this was the equation that comes from Coulomb's law that we talked about very briefly at the end of class last night. So this is the way to calculate the electric field on a point charge due to another point charge. If I don't have an electric field due to a point charge, then I've got an electric field due to something else, and this is my equation for calculating the magnitude. So again, I've got options here, not just in which direction it goes, but also in what equation I want to use to calculate the electric field. Next question is the object charged and moving in a magnetic field. So if that's the case, then I'm going to have a magnetic force. And B, even though this seems completely unreasonable, B is the letter that we use for talking about the magnetic field. So F sub B is a way of saying the magnetic force. So if I have a magnetic force, its magnitude will be given by the amount of the charge, regardless of its sign, times the speed it's moving at, times the magnetic field, times the sign of the angle between them. Again, this is all something that in the better part of about 6 weeks when we start dealing with magnetism, this is all something we'll worry about then. The direction will have a right-hand rule, just like what we had with torques in the first semester. There'll be right-hand rules to help us figure out the direction of the magnetic force. And so this is what we're going to add. And then we'll come back and say, hey, is there anything else exerting a force on the object? If the answer is yes, then we've still got an applied force. So this is sort of welcome to 222. So here's what we're going to add. Now a lot of times we'll just deal with electric and magnetic forces without worrying about the rest of it. And so one of the things we'll have to talk about in class is, when do I need to go through all 8 of these questions? When do I really just need to focus on question 6 or question 7? And there are some pretty easy ways to think about when that'll be. But we'll talk about all this in class. So you can think of this as sort of reminding you what forces are, reminding you that you know a lot about forces already, and then previewing where we're going to head in terms of what we'll add in thinking about forces this semester.